Thank you. Okay, do you see the slide showing the link budget calculation? You do? Guys, do you see the slide?
Yes, sir.
Yes, sir.
Okay. Well, give me a second. Let me quickly take the attendance today. Mahmoudul Hassan, what's your student ID? Mahmoudul Hassan, could you please tell me your student ID? I can't read the whole title here. Mahmoudul Hassan. Sorry. I'm just taking the record of your student IDs were present today. Mahmoudul Hassan, I can't read your ID. Okay, I'll now read out the IDs that I could capture. If your ID is not here, please let me know. Okay, if I miss your ID, let me know. 049 059 101 110. I'm reading out the last three digits. 110 113 115 116 104 124 136. From section A, is there anybody else?
So 104 present.
104, yeah, it is there.
1 to 4.
1 to 4, yeah, I said
124,
124.
sir.
Yeah,
Sir,
Present, sir.
I mentioned 124.
sir, 118, sir.
118. Who else? Okay. Anybody else? Anybody else? Okay, done. From section B, 205. And anybody else?
Sir, 17-59, sir.
59. Okay, you're from B. Yeah. Anybody else from section B? I don't think there is. Okay.
Sir, you stated that 49, sir. I am from 16 series.
049. You're also from section B. Okay.
Section A, sir. Section A.
Section A.
16
Okay.
series.
Okay. Okay. It's okay.
Thank you, sir.
Okay. Then
Sir, 218 from section B.
218. Okay. Thank you.
Sir,
Yeah.
229, sir, from section B.
229. Okay.
Yes, sir.
Anybody else? 229. Anybody else from section B?
139.
Mm-hmm.
So section A, sir, actually.
139 from section.
139, so section A.
Okay, okay. Okay. Now
Sir,
let me
sir, 115 section A.
115. Yeah, I mentioned this ID. Okay, now from section C. Well, I'm sorry, I won't. I'll read out, but not in order. Okay. 315, 329, the last three digits. 328, 330, 338, 301, 322, 323, 327, 312, 314, 336, 334.
So 314, sir. 314.
314. Yeah, I
Sir,
mentioned that.
305, sir.
Oh,
305. Okay, that
332.
305. 332. Okay. These two
Sir.
I don't have in the list. Yeah.
Sir, 331, sir.
331. Okay. 331. Okay. Anybody else from section C?
Sir, 325.
325. Yeah. Okay. Thank you. Okay. Anybody else?
Sir, 225.
225. Okay. Anybody else?
It's a 102, sir. আমি ভুলে ল্যাবের লিংকে ঢুকে পড়ছিলাম।
102. Okay. Who else? Okay. Let's go back to our presentation. Okay. The slide is again visible, right? Well,
yes,
for
sir.
the base station, we are calculating the minimum power that you need at the position of the receiving antenna. How much power there should be in the air. Okay. Well, let's assume that this power is M. Okay, M here. Now, the C by N requirement can be first said depending on your receiver sensitivity, how much CNR you can tolerate or allow. And this C by N, look at the top few lines. C by N is the ratio, but when you put them in dB, you have C minus N. The noise power, if we calculate from here using, say, K TB, Boltzmann constant multiplied by the temperature and the bandwidth. Then we have the bandwidth 30 kilohertz. See, look at the top right calculation here. 30 into e to the power 3, there's the bandwidth 30 kilohertz. And the temperature in Kelvin was 294.1, you see in the table. So we put that here, 294 is the temperature. And for Boltzmann constant, it's I mean, very low value. When you show in dB, then Boltzmann constant appears as a large negative number. Okay, and then you add this to their positive. Anyways, in so in dB, you get a value of minus 129.1. So that is our noise floor. Considering only the thermal noise. But in the receiver, I mean, there can be some other sources of noise. And so you have, I mean, that is the noise floor, or you can say that is the, I mean, that's the noise power level. Okay. So unwanted noise power level is this much. But because of other sources of noise, which is represented by the noise figure, your actual noise will be a little higher. So add this noise figure to that, and so you get the new noise power minus 125.1 dBm. So this is the unwanted power N. n for us, and it appears here as a plus b. Okay, c equals to a plus b. Now the desired power, we have here m. M is the desired power, but this power level will be can have little gain, like or you have some improvement in the power that you actually find in your circuit because of the receiving antenna gain. So A, that is shown here as K. Look at the rightmost column. This antenna, receiving antenna gain is K. So we add M, we add K to M. So that is the power effectively. Also, if we use some diversity gain, I mean, multiple antennas, I mean, we discussed the use of polarization diversity or space diversity. And because of that, we have additional gain of 5 dB. Okay, so the effective power can further increase. So
Sir, can I interrupt you, sir? Just for 1 minute.
Sure, anytime. Yeah.
So, sir, in this case, sir, while we're calculating the noise figure, noise floor, sir, these are from the basic formulas, right, sir? Like A is using this formula, and the noise floor is what we know from before, signal to noise ratio output by input.
Right. In
So,
fact,
sir,
for noise figure, as you keep like in the problem of our last class test, and when you keep your say signal power fixed, I mean, you here we are using the noise figure to have an estimation of the noise power only. Okay, the signal power we are calculating separately, but the noise figure we are using because you have some additional noise added, and that is what you indicate using the noise figure. Okay, so this additional noise you can calculate using this noise figure.
Okay, sir.
Okay. Now, what
So, sir,
did you have any other question?
Yes, sir. All these values, sir, that we are using in order to tabulate this table. So these will all be given in the question, sir. So we have to find one after the other.
They all will not be, but say, okay, I'll tell you what will be given. Like the channel bandwidth, this can be given. And for this particular, the way we are calculating here, this channel bandwidth will be given, the temperature, okay, and the these two, channel bandwidth and this two. From there you can calculate the thermal noise here. That is what you will have to calculate. And then the noise figure will be given, so you can calculate the effective noise power level. The cable length or how much cable loss. Okay, either the total cable loss can be given directly, or per unit length, how much loss you have. Okay, so somehow you'll be able to calculate the cable loss. The required C by NR will be given. I mean, for this, the way we are calculating here, it is given here. Okay. Now, the other vehicle or body losses can be given. Anyway, so when you have say diversity or gain or antenna gain, this should be given. So this is the power you have M plus K plus L. Okay, so all this includes some favor to the power level, but there will be some losses, like the power you capture in the antenna will be deducted because of the absorption of power in the cable, and so at the base unit you will get a lower power. So this cable loss is 1.7 dB here. You see receiver cable loss is 1.7 dB, and so that they calculated it for how much power cable loss you have for certain length. Okay. From there it is calculated 0.8 per 100 feet dB, 100 feet. So for 220 you have 1.7 dB. Okay, now this D we need to subtract, right? Our receipt power in the air M plus antenna gain K plus diversity gain L minus cable loss. Okay. Then there could be, if there are any other losses on the way, that should also be subtracted. So that is finally you get the carrier power at your receiver, okay, at the base receiver, and this is your N. So this is how you calculate C minus N, which we indicate as F. F is our C by N in the table. Okay, but let's manipulate and bring M on the other side, because that is what we need to calculate while F is given. So we bring F on this side, and then we get actually all the terms together this way: A plus B plus D plus F plus H plus I plus J minus K minus L. That's it. Well, few things we have combined here, like G is E plus F. Okay, so after combination, I mean, we have fewer terms here, okay, that you may do. Anyway, so probably the impact from different parameters are explained now for this column. In the next column, we would like to determine how much power should be available in the downlink at the receiving end. So the receiving end is the EEE, the mobile device. So what power you should have in the AR where the EEE antenna is located? Well, again, we determine the same way, but you see some losses are little different. Okay, like now we don't have the cable loss. In the case of base station, the antenna can be located at the top of the tower, but your actual equipment is located at the base, and you connect them using a cable. So the cable offers some loss, which we show as cable loss. But in the case of mobile, your antenna is directly connected to your device. There is no cable in between. So the cable loss is absent here, right? So this, in this fields, you have nothing. However, you can have some losses here when your mobile receives, like your mobile, I mean, you put next to yourself, and your body consumes some power. Okay, I mean, maybe if you assume that you put it on one side and the power comes from the other side, somehow you actually are like hiding your mobile using your body. Okay, so your body consumes some power, and so you show body loss. Or you may be inside a vehicle, so the vehicle absorbs some power, so you have some vehicle loss here. So these losses can be there, but these sort of losses you don't have in the case of base station. When the base station receives, I mean, there is, you don't put the base station inside any car or something, right? For mobile, there could also be in-building losses. Okay, you may be inside a building, and these losses are shown here 0 dB though, but it could be there. So if it was there, I mean, you should of course subtract them, and so minus D minus H minus I minus J, all these losses should be shown here. In the case of mobile, D, H, I, J may have some values, but D should be 0. For the base station, D has values, but H, I, J are 0. Okay. So anyway, here also after you put the necessary values, you get certain power, and that is minus 97.1. Okay. Whatever values they are given lead you to this value. So these are the requirements, and considering the receiver sensitivity or the requirement of your CNR at the receiving end, you determine how much power you need at in the air at the position of your receiving antennas. So this is the first part of your link budget calculation. Now using these power levels, we'll use the final calculated power levels we'll use in the following slide to determine how much power you need from the transmitting end. But this one we will do first for the uplink. Why is it so? We previously explained that the uplink can get power limited because your mobile has some limitation in transmit power capabilities. The base station may have ample power for transmission, but the mobile doesn't. Mobile may not. Okay. So here we first put here that minus 125.5. It's about uplink. Okay. So you see in the uplink at the base station receiving end, you need this much power. So how much power you need at the receiving end? Put that for uplink minus 125.5. Okay. Now you check how much power the mobile can transmit. It was given in the question, it was given in watt, 0.6 watts. So you calculate in dB, 27.8 dBm. Then cable loss, no. For mobile, you don't have the cable loss. Okay, my internet is creating problem. Well, for mobile, you don't have cable loss or other type of losses. The combiner is a we explain this sort of connectors, okay, in the micro engineering course. Okay, I mean you have them to connect antenna and its components. Okay, so and you have them in at the base station, not in the mobile. So this loss you don't have here. The antenna gain for mobile is shown, but it can be considered just 0 dB. So the total EIRP is 27.8. You are transmitting power from the mobile end with this much EIRP. Then show the losses. The vehicle and body losses will also appear for transmission from the mobile end, okay, like 3 dB and 5 dB. So these data are given in the question. Assume that these body loss, vehicle losses are given in the question. So this, when you transmit in the uplink, again, the power goes through your body or through the vehicle. So you have again losses. So subtract these losses. And then also we need to allow some fade margin, okay, to ensure that the fluctuations of the signal level don't cause the receive power level fall below the requirement. Okay, allow some fade margin. So you also subtract, treat it's like a loss. We explained before that it's not really loss, but you need to actually treat it like a loss. Okay, it's just a provision of margin. So subtract them, and then you get how much power you have at the mobile end, at the transmitting end in the uplink. So 14.4 dBm is the effective transmit power available, and at the receiving end you have the requirement of minus 125.5 dBm. Now just subtracting these two, you can calculate how much power loss you can tolerate on the way. Okay, so once you subtract, you guess this power, and that is nothing but path loss. So it is the maximum path loss, the maximum path loss that can be allowed to ensure that you have sufficient power at the receiving end while operating at the full transmit power capacity. So the path loss can be 139.8 dB at the maximum. Now we work on the downlink, because we know that the uplink can get power limited, and that can allow a maximum path loss 139.8. So the downlink, to maintain path balance, previously we called it path balance in our previous slides. To maintain path balance in the downlink also, we will use the same maximum path loss. So 139.8 dB you set here. From the previous slide, you take how much is the power you need at the in the downlink at the mobile end. At the receiving end, how much power you need at the in the downlink. That is minus 97.1. So this is the minus 97.1 is the power you need in the downlink at the receiving end, and then you have this much path loss allowed. So now you can calculate what is the transmit power requirement at the base station. Okay. So add to that this path loss, you add, and then you can calculate the required power level. So it is then 42.7. 42.7 is the transmit power at the base station. Well, but that is the effective transmit power. To get this power out of your transmitting antenna, there you need to consider other losses. So the power amplifier, which is located at the base, not at the top of the tower. Okay, in this example, I said that the power amplifier can also be placed at the top of the tower. Then it is called tower mounted amplifier, TMA. In the case of TMA, you don't have any cable loss. You can avoid cable loss, but you have to have enough I mean maintenance, okay, or proper I mean the amplifier when you set there, it has to be properly equipped. Okay, so it is simpler to have all the circuitry at the base, including power amplifier. Okay. So TMA is a little more complex, but it can avoid cable loss. So in this case, we don't have TMA, so we have some cable losses. So at the power amplifier output, you have 42. Well, no, now it's a back calculation. Now it is a back calculation. So again, you allow fade margin. Okay, and with that, you can calculate how much power you need. Okay, so after you add the fade margin 5.2, 5.4, you get 48.1. So that is the requirement of power here, 48.1. In watt it is 64.4. But you actually can subtract the antenna gain. That will help the power. That helps the power improve. Okay, but then you need to subtract minus 12, subtract 12, but then you need to add the losses. Okay, so that increases your power requirement. So with that you get 42.3. So that is the power you need in dBm at the power amplifier. So in watt it is 16.9 watt. So eventually you calculate actually how much power you need at the base station transmit equipment, and that is 16.9 watt. Okay. In this example, we are actually I mean, we don't have any given information of the distance between the transmitter and the receiver. That we just determine how much can be to maintain path balance. But the link budget calculation sometimes work in little different ways. Like you assume some transmit power levels, and with that you can determine using the link budget calculation, using put all these different values. Okay, this link budget is basically a rigorous calculation, considering even the small losses, how much power you need at the transmitting end, or for certain how much certain power level, how much the distance can be. So it depends what you really need to calculate in practice. But the link budget is a calculation of the whole wireless link, considering all different components. Okay, components of both losses and power improvement, like diversity antenna gains are power improvement factors, while cable losses, body losses are some loss components. Okay, for the whole wireless link, you consider all the different types of components and calculate one of the unknown parameters. So for either satellite link or for mobile link or for Wi-Fi, for any wireless link, okay, even for wired calculations, so there can be sometimes link budget calculations. So for a communication link, you have a whole calculation and a budget, how much power requirement or distance, for some parameters you have a calculation and some budget for your estimation. So that completes this link budget calculation. Questions?
No questions, sir.
Okay.
Thank you.
Well, it's 8:11. I wonder if we should finish in like 15 minutes today, because some of you may feel like joining the Asia Prayer in congregation, which is in most places at 8:30. What do you think? Should we finish little before 8:30 today?
So if you want to finish, it would be really helpful, sir. It's been a
Okay.
very tiring day, so we all started at 9:15, sir.
Yeah, yeah. Okay, we have another week in hand, and so inshallah, the rest of the stuff we can finish comfortably in the next week.
So is there a lot left for the last week?
Not left. We'll have a very brief discussion. I mean, now we will discuss. I mean, we'll begin one presentation. Basically, have I mean, this one has a medium length, but
Yes,
thereafter we'll have a very short 2 presentations. Okay, that's it.
Okay.
Is there any way to say concising these topics? Because in the last week, it's always hectic in the last week.
Right. In the last week, that the rest of the 2 topics, the topics I actually decided for the last week, I mean, are already very concise. Okay. I mean, considering the last week. Okay. So inshallah, we'll comfortably finish them. We'll have a brief introduction of MIMO. Okay. And brief introduction of infrared communication. That's it for in the last week. Okay. And today we're beginning at this topic, but actually we cannot finish today. The last part of it also we'll have to discuss in the last week. Oh, give me a second. Okay, in wireless communication, the use of statistical analysis is very common. Okay, so we'll touch upon its use. Okay, we won't have very extensive discussion, but we'll see some examples. Like very often, you'll see the use of Gaussian distribution, and you know that it uses. We'll have a brief discussion on this Gaussian. You may have covered in other courses though. Okay, so it may be just a reminder then. You know that it is a natural distribution actually. I mean, in the when you have ample sample size, okay, so gradually it converges. In the nature, when you generate IID, I mean the independent random variables, okay, they're completely random and they're independent of each other. the say when you throw the dice, okay, what you have in one of the throws does not affect what you have in another. So they are independent of each other. So for this type of independent random variables, when you try to get very large sample size, okay, then if you want to determine what may be the values, okay, they take on the shape of Gaussian distribution. So the larger the sample size, the better the distribution function, the probability function will look like the Gaussian distribution. Okay, so you know it will look like this. Like if you and it has a mean. Okay, the mean is the mu. Okay, if so, fx is the probability function, and mu is the median of the parameter value that that you are determining, for which you are determining the probability. And here sigma represents the variance. Well, you guys actually probably know better than I do. And maybe we really just go to an example. Like if you have some say you have some parameter which can take on different values, okay, and this is the mean value out of all different possible values. So you have random and independent properties for your samples. So what will happen if you have really large number, if you really have Gaussian distribution for probability, then say to get a value within this red range, okay, this is the mean value, this may be say 100, okay, this is 100, and here the last point of red may get 106, as let's assume on this side it is 94. Okay, so you may get many different values, and vertically you are showing the probability, how much the probability is that you get this particular value, you get this particular value. So you guess Gaussian distribution gives you the probability to get certain value for your parameter. Now the value to get the value within this range between 94 and 106, okay, you have this much probabilities. So if you calculate the whole area, the red part, okay, of course if you calculate the total area under the whole distribution function, it will be 1. Okay,
yes,
so if you calculate this red part, it will be actually 0.68, meaning that 60% of your parameters value will lie between this range 94 through 106. Okay, and 95% of the time they will lie within this range, say what is indicated by the green. Okay, so that may be say 88 through 112, just to give you some examples. But in fact depend, it depends on the variance. Okay, so this red part is mu minus sigma through mu plus sigma. Green part mu minus 2 sigma through mu plus 2 sigma. Okay, that's 95%. And then if you go up to 3 sigma, then 99.7% part you capture. Okay, most of the values you already capture. The calculation can be made easier. The actual function is given this way, which has x minus mu. X is the value of your parameter, mu, median, variance. Okay, so taking the whole distribution, it must be 1 when you integrate over the whole range. Okay, from minus infinity plus infinity. Okay, and But the calculation can be easier by assuming this one z x minus. So then you have only z here. Okay, the function looks easier. And for this function, there's already a table. You don't have to calculate. You don't have to calculate. Okay, like let's use. I'll give you a. If there is any problem relevant, I'll give you a whole chart for this z function. Okay, like if you calculate, if you need to calculate for a case like where the birth weight, the average birth weight is 109, and I mean for all the samples, okay, what the averages and the variances should be known beforehand. So the variance here is the standard deviation.
But sir, our denominator will be the standard deviation.
Standard
right,
deviation, yeah, it is the standard deviation, right?
Root over of the variance.
Root
sir.
over the variance, yeah.
Yes.
I was little mistaken. Root over of the variance is the standard deviation.
Yes.
So it is 13, and median is 109. So the question is, what is the is for the weight of the child when it is born? So the question is, how much is the probability that the weight is 141 or larger? Okay, so when you just determine z, it is 2.46, and for this 2.46, for this 2.46, okay, I mean, look at this example here. For we are calculating the value of say z is set here 1.51. So to get the probability that the value can be 1.51 or lower, okay, we actually need to integrate this whole area. And this value, how do you get? Well, from this table, z is 1.51. So from this first column, find out 1.5. Then from the next column, pick 0.01. So it refers to 1.51. Then you get a value 0.9345. So the whole area on the left to this 1.51 is 9.9345, or I mean there is 93.45% chance that the value falls below this level 1.51. Similarly here, say the value 2.46. Okay, for 2.46, if the table actually is incomplete here. For 2.46, the value can be 0.9931. Okay. Now the question is, what is the probability that you get the weight larger than this value? So we actually need the rest part, the value above this limit. Okay. So one minus 0.9931. So there is actually 0.69% chance only to have this much weight. Okay. So this sort of calculation is another example. Okay. Anyway, so I think we can finish today. We'll finish this presentation the next day. Okay. So, it is.
Speak of these questions, like population-based questions.
It is just an example. We will use it for actually calculation of our say outage probability. Okay. I just wanted to make you familiar with this Gaussian distribution calculation. So, but we'll be using it to calculate that for certain. Say you want to make sure that you have some requirement of minimum power. We know that using link budget we are calculating minimum power requirement. But in the field, it doesn't work black and white. You can say that, well, with this much transmit power, I'll get this much power over there. No, you will get actually random values or some. I mean, it will follow some statistical nature of what you really get at the receiving end. Okay. So using Gaussian distribution is popular for this determination. So you calculate, okay, then how much is the probability that the power there does not fall below this minimum requirement? Okay, you set a minimum requirement, but the value can be different at different times of the day. You will get many different values. Okay, so in your engineering design, you set it according to your design, but the value can be a lot different. So how much is the probability that the actual power can fall below this minimum requirement? So you can calculate using some statistical distribution, which may be Gaussian. Okay, we'll use the Gaussian distribution for our example. And that will give you a probability of outage. If it falls below, then you go out of coverage. So how much is the probability for this out of coverage? Okay, you don't have to make sure that the probability is 0. No, as an engineer, you have a balanced design. Okay, the outage probability should be below a certain level, and then the design is fine. Okay. So next day, inshallah, we'll discuss it. And we'll also touch upon Rayleigh fading and Gaussian fading. Okay. Anyway, yeah.
Sir, I'm ID 222.
Oh, you are okay. What is the ID 222? Is there anybody else?
Because of the rain.
Anybody else?
Sir,
Whom
sir,
I
203, sir.
Sir, 109, sir.
Sir, 203, sir.
203.
302.
302.
Sir, 229.
227.
And please, one by one.
116, 234.
116 is there. Huh?
Sir, 207.
234. Who is next? 333.
333, sir.
Yeah. Okay.
339.
339. Okay. Who else?
Sir, 203, sir.
203. Yeah, I have written.
207.
207. Okay.
So 323.
323.
210.
210.
326.
326.
Sir, 324.
324. Okay. Okay.
Sir, 130.
Sir, did you
One.
Sir, did you hear 222?
220. Yeah, I did.
Sir, 222.
220. Yes, I did.
Sir, thank
Sir,
And
130.
130. Okay. 130. Hmm.
Sir, 108, sir.
108. Yeah, I didn't have it in the list.
205.
Sir,
205,
116, sir, 116
Yeah.
get disconnected, sir. Is he
Yeah.
present?
But yeah, 116 I have in the list. 205 also I had in the list. Anybody else? Okay.
225.
225. I had it in the list.
139. Do you
Mhm.
have 139? Do you have?
139. I had it.
Sir, did you get 115, sir?
15. Yes, I got.
Sir,
Okay.
Sir, about the mid marks, are you going to? Give?
Oh, I'm so sorry. What happened? I mean, I had illness, and when I recovered.
Whenever you feel comfortable.
Yeah, when I recovered, I mean, I actually got off new assignments from the department, and I mean, barely I could support the department, and anyway, so inshallah, every day I plan to grade your scripts, but at the end of the day, I fail. But I again plan to do it as soon as possible. Okay.
Okay, sir. Thank you, sir.
Thank you so much.
221, sir. Third list, sir.
221. 221 I didn't have in the list. Thank you.
Yes,
Thank you for telling me. Okay. Wa alaikum assalam.